Okay, take two. Let's hope this works. So we've got f dash of x equals 0 as the turning point. And so what we're really doing here is we're saying, I know that at x equals 0, I've got a turning point because f dash of x is equal to 0. And therefore we have in terms of the gradient, we have a stop. So if I now look at a point either side like so, and that's arbitrary. I can choose any number really. I can then substitute that into f dash of x because it's an easy function to do so and see what's going on. So if I substitute -1 for x, I get -2, so that's negative. And if I substitute 1 for x, I get 2, which is positive. So a negative gradient means the graph is going down, and a positive gradient means it's going up. And we can now see from that shape that is a minimum. I know we know this because we know what f of x equals x squared looks like, but I'm just confirming it. Okay, so that's the first derivative test. And the second derivative test doesn't always work, so it's important to know the first derivative test. The second derivative test goes one step further, goes f dash dash of x is equal to, and then it finds the derivative of 2x. So it's the derivative of the gradient function, which is equal to 2. Okay? So what does this mean? It means that the gradient of the gradient function is constantly increasing. It's not increasing, so it's constantly positive. It's a constant gradient of 2. So if this is f of x, okay, wish me luck with this, then this would be f dash of x. Okay, it is its own function, and as you can see, it's increasing from left to right. The graph is increasing. Okay, so because of that, because we can see that after 0, because we know that it's increasing and it has a 0 here, we can see that it goes from negative to positive here. Okay, it's always positive, so it's always going up. So therefore, when it gets to a 0, in this case it happens to be 0, 0, it's going to go from negative to positive. In other words, this perfectly captures this. It must go from negative to positive because its gradient is positive. Okay, the values must go from negative to positive because its gradient is positive. There's no other way you could interpret it. Right? So the gradient has a 0. In other words, its function cuts through the x-axis here. So the gradient is here. It's linear, and so it either has to go from negative to positive or positive to negative, right? Because it's not going to change direction. So if it was going from negative to positive, it would have a negative slope. Sorry, if I was going from positive to negative, it would have a negative slope. If it's going from negative to positive, it must have a positive slope. So the second derivative automatically tells us what's happening here and here. The second derivative is positive, which means the gradient of the first derivative is positive, which means it must be going from negative to positive. And what does that mean? It means that it must be a local minimum. Okay, so it's a follow the breadcrumb trail. That's the theory behind it. I guess the practice is trying to memorize it, I suppose, if you can't get the theory right in your head. And the practice is, if the second derivative is bigger than 0, it's a local minimum, which seems counterintuitive, but maybe another way of putting it is, if the second derivative is positive, it's concave up, and up always feels positive, it's a smiley face. If the second derivative is less than 0, i.e. the second derivative is negative, then it's concave down, frowny face. which would give you a local maximum. And if the second derivative is 0, it's inconclusive. Go back and do a first derivative test. Okay. Anyone got questions on that? Okie dokie. So that brings us on to today's work. Now, just conscious of time, I'm going to just skip ahead a little bit to the practicals. So I want to show you that on your schedule of work, this is Monday's work. There are videos here. This one here, I think we might have seen before, but it's therefore it's a re-explanation of what E is and the special properties of E. 3 Blue 1 Brown does a really good explanation of the calculus of E. It's a bonus video. This one here is from Khan Academy, and Khan explains the derivatives of, I hope it's the derivatives of ln x, I think. I don't know, I've got powers there. And we've got an Eddie Wu special as well. What's wrong? Is that...
Your notification.
I was doing it again.
Is Eamon your son?
Yeah, he's my son.
He's got PE tomorrow.
Oh yeah. Do you think if I didn't have a reminder that I would remember? Do you think he would remember? He's 10. Sorry, I should have. Normally, when you put Vivi on, the notifications don't.
Yeah, earlier it came up. We saw some notifications, and then it flipped and went, "Will not show details when screen share."
Oh man, now it won't click on the do not disturb. Sorry, so I can't get that off.
It's all different to ours. All the apps are nicer. His is better. His is. Yours is probably allowed to update.
Yeah, I'm running on beta. Okay, so there's some videos there to support what I'm about to show you, which is just the most rough, bare bones thing ever. I left my notes back in the thing. Okay, so here are some notes for you to take down.
It looks so much nicer. It's like an iPad. That is that.
And it's slowed down again by the looks of it.
Yeah. Wait, why does your iPad have apps down the bottom? No, that's his computer, and one thing's on his iPad, and it just looked like it was his iPad because he was using the iPad and it was moving on the screen, but it was just going slow.
Okay.
What we can see is his computer.